In the last lesson, lesson 4, we talked about exponential growth primarily and exponential functions. We saw that the exponential parent function is essentially y equals a times b to the x, where a stands for the initial amount, which is also kind of like the y-intercept. B stands for the rate, which is the number that we multiply by each time to get to the next number. X and y were variables that would correspond to something on the Cartesian coordinate, but generally x stood for a time amount if this were some sort of real-life problem, and y stands for the total amount. Now, today we're going to look a lot closer at the difference between exponential growth and exponential decay. And so ultimately, the purpose behind this is to get at a lot of real-life problems that either grow exponentially or decay or go down exponentially. There are many connections here to real-life things. So here's a couple things. The contrast between exponential growth and exponential decay. Now, both of these formulas are based off of our original y equals a times b to the x. Exponential growth is y equals a times 1 plus the rate to the t power. Okay. Again, a still stands for the initial amount, r stands for the rate in this case, but typically what will happen is you'll be given a percent increase. So maybe something grows at 5%, okay, the rate would be 0.05. Now, if I want something to increase by 5% or 0.05 each time, I can't multiply it by 0.05 and make it get bigger. And in a sense, what's happening here is you would need to turn this into 1.05. If I multiply something by 1.05, that will make it grow by 5%. And so that's why we see this plus 1 here. Okay? Now, if I take a look at exponential decay, and I want something to decrease by a certain percent each time, then we'll have y equals a times 1 minus the rate to the t power, where t is time, usually in years. And so what you see here is that, again, if I wanted something to decrease by, say, 75%, well, what's going to happen is 0.75 is 75% as a decimal. And then if I take 1 minus 0.75, I'm going to get 0.25. Okay? And so if you are decreasing something by 75%, say you had something that was $100, if you're decreasing that by 75%, that would wind up giving you, well, $25. You would be keeping 25% of it. Okay, so the key phrase here is like with this, you're going to keep, or how much remains is 25%. Okay, and that's what this 1 minus the rate does for us. The a is still the initial amount, and the t is still time. Okay, so it's just some of the basics. Number one, graph this function in exponential decay, and then identify the domain and range. So this is one of the direct I can statements that you'll have to perform on a test or a group test. Okay, so in this case I have y equals 1/3 to the x power. Now I don't have an initial amount, so we have an invisible 1 here. And again, if you drew a table, which I would suggest doing, then if you have x equals 0, anything to the 0 power is 1, And so we can see that my y-intercept is 1. Okay? So we'll just create an interval here. Alright, let's pick a couple of numbers to plug into this formula and then graph. If I pick 1/3 to the first power would be 1/3. And so you can see here that it's definitely not going up, it's going to go down. So when x equals 1, y equals 1/3, that'd be right around here. Now again, remember with exponential functions, this is a pattern. I'm multiplying each by 1/3 to get to the next number. So if I wanted to keep going, go x equals 2, I don't really have to plug in 2 here, I just keep going with the pattern. And 1/3 of 1/3 would be 1/9. And so if I had 2, it would be a very small 1/9. And you can see that it's going down, but it doesn't matter how many times I divide this by 3, it's never going to be 0 and it's never going to be a negative number. Now if I want to go the other direction, so say I go -1, instead of dividing by 3 like I did here, I would multiply by 3. And so 1 times 3 is 3. So if I go here in the other direction, -1, I'm going to have +3. And that's about enough to my function, and there it is. So you'll get a lot of practice of doing that. I suggest using tables. I would suggest not necessarily plugging in numbers here, but I would suggest using patterns, multiplying to make the number go bigger or dividing to make the number go smaller. Okay, so that's graphing exponential functions. One of the other I can statements is writing a rule for an exponential function. So here, again, I have exponential decay. I've been given 2 coordinates. I have 0, 2, and then I also have 2, 0.10. Okay, well, here's how this is going to work. When we write an exponential function, we want it in y equals a times b to the x. We need the initial amount, okay, in this 2, so I have y equals 2. Now what I don't know is the rate, okay? So at this point, I can pick, really any of these points that are on my line. I'm going to pick, well, let's see what happens if I pick 0, 2. I'm going to put 2 in for y, 2, I still don't know b, that's what I'm trying to figure out, and then my x value is 0. Now, b to the 0 power, that's 1, and so 2 equals 2, well, that doesn't really help me out. I wasn't able to solve for b. Okay, so this is kind of a dead end. I think we're going to have to use that one right there. So again, we'll plug things back in. We'll say y equals 0.1 equals 2 times b, and this time the x value is 2. Alright, well, if I go ahead and try to solve for b, remember we're doing the reverse order of operations. I'm going to divide both sides by 2. And so if I take 0.1 and divide it by 2, I'm going to get 0.05. So 0.05 equals, these have canceled out, then I have b to the 2nd power. In order to get rid of that squared, I'm going to take the square root of both sides. And so when I take the square root of 0.05, I wind up with b equaling 0.22, we'll call it 0.22. Alright, so as I now have this last piece of information, I'll put this all back together right here. I have y equals 2 times 0.22 to the x power. And there is my function that matches this exponential graph. Now, like I said earlier, back when we first started, exponential growth, exponential decay, these are used for real life problems. So here, I've made a new one. You receive $5,000 for your 14th birthday. If you invest this in a company that earns 12% per year, will you be able to retire at the age of 54 with $1 million? So remember we want to set this up, and so if we want y equals a, okay, this is growing exponentially, so 1 plus the rate to the t power. This is the formula we're going to use. Well, the original amount is 5,000. The rate is 12%, so 1 plus 0.12 would be 1.12. And until you're 54 years, well, that would be 40 years. Okay? Feel free to use your calculator at this point. So we've got 5,000 times 1.12 to the 40th power. And although it's a lot of money, we have y equals 465,254. It is not $1 million. So no. Now, a follow-up question here, and one of the other I can statements is solve exponential equations. This is essentially where that's going to come into play. So what rate would you need to solve by in order to get this information, or to get $1 million? Well, the final amount would be 1 million, so let's plug that in for y. And then we'll say A, the original amount was 5,000. What we want to know is the rate, B, and then to the 40th power. Okay, so we'll take 1 million now, divide it by 5,000, and you've got 200. So now we have 200 equals B to the 40th power. And this is a little bit tricky, but we're going to take the B to the 1/40th power, or 200 to the 1/40th power, or the 40th root. Okay, so B, and so if you're, well, we'll take the take 200 to the 1 divided by 40th power, and you get 1.14. Okay, so we don't want this 1 here, that's not part of the rate, but the rate is 14%. Okay, and then finally, how much at 12% would you have to invest originally? So the setup here is we would want $1 million still. And then what we don't know is the original amount. We do know the rate is 1.12, and then again to the 40th power. Okay, here simply you're going to take 1.12 to the 40th power and then divide. As you can hear by the bell, I gotta go. So there it is.